This unit is about curve fitting. You'll be investigating data points, like the red ones shown here, and you'll be trying to find functions whose graphs provide a best fit with the data. You may choose to focus on straight line distances from points to the line, as shown here, or you may choose to focus on squares to these distances. But, in either case, you need to be able to make fancy curves using simple curves. So, this is what you'll be learning to do in this homework assignment. One of the simplest functions is a constant function like y equals c as shown here. And, as we change the value of c, this graph shows the result. Next, let's look at the graph of the function y equals b times x. As you change the value of b, the slope of the graph changes. But, it continues to go through the 0, 0 point on the graph, and also the point 1b. Next, let's combine these two simple functions y equals c and y equals b times x, and let's look at the graph when we add these two functions. For the function y equals c plus b times x, notice that the black line is always parallel to the green line and it always intersects the vertical axis at the same point as the red line. And, notice that the graph of the black line is y equals c plus b times x. Next, let's look at the function y equals a times x squared. Notice that, as the value of a changes, the yellow square always goes through the point that is a's inverse. So, the corner of the square is at the point 1 over a on the horizontal axis. Then, notice that the blue parabola always goes through the corner of the yellow square. So, when the value of a changes, the shape of the blue parabola changes. Now, we're ready to examine the sum of the three monomial functions. Y equals ax squared, y equals bx, and y equals c. So, the sum of these functions is y equals ax squared plus bx plus c. And, its graph is shown here as a black parabola. Notice that the black parabola is always exactly the same shape as the blue parabola. But we can move its location to other places just by changing the values of b and c. So, by investigating what happens to the black graph when the values change for a, b, and c, you can get a feel for how to make the black parabola go through other points we choose. Next, let's investigate what happens when we multiply two linear functions. To begin, let's graph the two functions. Y equals ax plus b. And y equals cx plus d. Then, let's graph the product ax plus b times cx plus d. The result is a parabola. And, it crosses the horizontal axis at the same points as the two lines. So, change the values of a, b, c, and d and investigate how the shape of the parabola changes. This is another way to move a parabola to other shape and location we choose. So far, in this animation, you've seen how to make polynomial functions in two ways. First, by adding monomial functions. And second, by multiplying linear functions. Then, in another activity in this section of the course, you've also seen how to make parabolas a third way, that is, by accumulating linear functions. Furthermore, you also have seen how to make linear functions from constant functions. So, you've seen a variety of ways that more complex functions can be built up out of simple functions. And, this is very important when you're trying to describe complex situations by breaking them down into their component parts. Because so many situations can be described using sums, products, differences, or quotients of linear functions, it is useful to know how to write the formula for a function whose graph goes through any 2 points, such as a, b, and c, d shown here. To find the function of the line that goes through these 2 points, begin by drawing the line that you want. Consider the xy coordinates of any point on this line. Then, notice that the triangle whose vertices are xy and cd is similar in shape to the triangle whose vertices are ab and cd. So, d minus y divided by c minus x is equal to d minus b divided by c minus a. And, this proportion can be transformed to the function shown at the bottom of this worksheet. So, This is the function whose graph goes through the points A, B, and C, D. Now, another capability that is useful is to be able to take any function and stretch it, shrink it, or move it in any directions that we choose. And, to see how this is possible, it is useful to quickly investigate another important kind of function, which is called a repeating function, or a cyclic function. For example, let's look at the sine function. One way that sine functions results from a cyclic event, such as when a point moves around a circle, as we will show here. In this animation, notice that the two red line segments are exactly the same size, and also notice that the blue segment is exactly the same length as the blue arc on the circle. Now, let's run the animation and watch the path of the point P'. This path is called a sine curve, and it's denoted in this way. Y equals sine x. Now, let's investigate this slightly more complex version of the basic sine function. The values of A, B, C, and D are determined by the sliders shown on the right side of this worksheet. So, when you change the sliders, the graph at the bottom of the worksheet will change too. Notice what these changes do, because we'll be able to use them for many functions, not just sine functions. What does the value of A do? What does the value of B do? What does the value of C do? And what does the value of D do? Or, think of the symbolic versions of these same questions. What does B do? What does D do? What does A do? And, what does C do? For one activity in this problem set, you'll be using these ideas to make graphs whose functions are all based on the same basic function. Y equals x to the nth power. The more complex version of this functions looks like this. And, if you change the values for n, you can make graphs which have any of the shapes that are shown. And, if you change the values for A, B, C, and D, then you can move or stretch these graphs in any way that you chose, when you are trying to find a graph that fits some collection of data.